All right, welcome to Math341, Lecture 17. What we're going to do today is we're going to continue with the method of differentiating identities. It is such a powerful method. It solves so many different problems. It is worth really going through and describing in great detail how to use it again and again and again. The other thing is, at the end of the day, we're going to spend a lot of time looking at the normal distribution, the Gaussian, the bell curve. Anything with this many names is important. You have a couple of fundamental theorems, the fundamental theorem of arithmetic, of algebra, of calculus. We don't say fundamental, we say central for this course. It's one of the big ones. We will first prove that it actually is a probability distribution, that it integrates to 1. And we'll show some nice techniques as to how you do that. All right, so let's first start off with Poisson random variables. So, using the method of differentiating identities, this just provides a nice vehicle to go through some of the standard distributions. So we'll say x is Poisson with parameter lambda if the probability that x equals n is e to the minus lambda, lambda to the n, divided by n factorial, and n is in 0, 1, 2, 3, going off to infinity. All right. Can anybody give me an example that's modeled by the Poisson process? Uh-oh. All right. Anyone give me an example of a Poisson process? So if you've taken a stats class before, you've hopefully seen this used at least for something. Where's maximum likelihood of Poisson process? Maximum likelihood is a technique you use. Yes? Number of births in a hospital. That's much nicer than the number of accidents at an intersection. I think they often use like number of deaths of German soldiers from horses. I think that's the standard one that you often use. So whenever you have this, it's not enough to just specify what n is. You also want to specify what is lambda. So lambda is just any number that's greater than 0. If lambda was less than 0, then whenever n is odd, we would have a negative number here, and we'd have a negative probability. Right? If lambda equals 0, this is an extremely degenerate case, then all the probabilities would be 0 except n equals 0. You would then have to interpret 0 to the 0. You would interpret that as 1. And if n equals 0, it's essentially nothing happens. Okay, so the first thing is, it's non-negative. We need to show that it sums to 1. So if we sum, n goes from 0 to infinity of e to the minus lambda, lambda to the n over n factorial. Well, we can pull out the e to the minus lambda, because this has no independence. So this will be e to the minus lambda, the sum n goes from 0 to infinity of lambda to the n over n factorial. Does anybody recognize what's in parentheses? This is just our Taylor series for e to the lambda, right? 1 plus lambda squared over 2 factorial plus lambda cubed over 3 factorial. So we get e to the minus lambda times e to the lambda, which is 1. All right, so it is a probability distribution. And so we could try to calculate now the mean. So if we want the mean, then we want to calculate the expected value of x. So this would be the sum, n goes from 0 to infinity, of n, e to the minus lambda, lambda to the n, over n factorial. It's not terrible to calculate this. You have to do a little bit of algebra. Any thoughts on what we might want to do? So how might we do the algebra for this? I've got an n, e to the minus lambda, lambda to the n divided by n factorial.
You could cancel the n and try to shift the indices.
Yeah, I could try to cancel the n. So if I cancel the n, I would have an n minus 1 factorial. I'm not really happy about that when I start off with 0, because I would have negative 1 factorial. It turns out negative 1 factorial actually equals... I'm sorry? No. Negative 1 factorial equals infinity. So we might talk a little bit about why that's true, but it would be much better to just say, what should I start this sum at? I can start the sum at 1, because if I put in n equals 0, then n factorial down here, I interpret that as a 1, and I've got a 0 here, so I can interpret this as a 1, and this is now a sum, n goes from 1 to infinity, of e to the minus lambda, lambda to the n, over n minus 1 factorial. And now if I just pull out a lambda, I would get a lambda, the sum n goes from 0 to infinity of e to the minus lambda, lambda to the n minus 1 over n minus 1 factorial. And that's basically just, I've shifted, n goes to 1. That just sums to 1. And just, instead of using n as my index where n goes from 0 to infinity, I'm using n minus 1 as my index, and it goes from 1 to infinity. So this part in the sum will just be 1, and you'll be left with lambda. So we are able to calculate this by doing algebra. We can also calculate it by using differentiating identities. So we know that the sum, n goes from 0 to infinity, of e to the minus lambda, lambda to the n, over n factorial equals 1. So the hardest part when you do differentiating identities is you have to find an identity to start with. Then you have to differentiate it. Yeah. The name is pretty self-explanatory as to what you do. Find an identity and then differentiate it. Well, I could take the derivative of both sides with respect to lambda, but I might not be thrilled about that because I'd have to use the product rule. If I move the e to the minus lambda over to the other side, now I no longer have to do the product rule. So this is a common technique in all these problems, is just move something over to the other side, and now I have the sum n goes from 0 to infinity of lambda to the n over n factorial equals e to the lambda. And then at the end of the day, when I want to get my probabilities, I then just move the e to the lambda back. But by doing this, I avoid having to use the product rule. So now I apply lambda d by d lambda. And I would get a sum, n goes from 0 to infinity, of n lambda to the n over n factorial. And what do I get on the other side when I apply lambda d by d lambda to e to the lambda? Derivative of e to the lambda is e to the lambda. So I just get lambda e to the lambda. Now if I want to calculate the mean, this is not quite what I need. I need an e to the minus lambda. So I multiply both sides by e to the minus lambda, and I would get the expected value of x is the sum, n goes from 0 to infinity, of n lambda to the n e to the minus lambda over n factorial equals lambda. And there's the mean. If I wanted to calculate the variance, I'd need the mean squared, got that. And then I would have to calculate the expected value of x squared, so I would just take another derivative. And so when I apply lambda d by d lambda again, now I have to use a product rule over here. It's not terrible. So I'll leave it as an exercise to finish the calculation and compute now what would the variance be of a Poisson random variable. Okay? This is a calculation you really want to know how to do. You can compare that to doing the algebra and playing the games of shifting the sums. All right. So the next distribution I want to look at is the negative binomial. This is not as popular as some of the other distributions, though it should be. Out of curiosity, how many of you have done the negative binomial? All right, not as many. And I wrote down notes to make sure that I do not do things incorrectly. So what I want to do is negative binomial. So the number of successes before we get exactly our failures, with probability of a success equals p, and the probability of a failure minus p. So r is a fixed parameter. So you could say, x is negative binomial r p. I have to give you two numbers. How many failures I want to have, and what's the probability of a success. Okay? So we want to calculate what is the probability distribution. What kind of values can R take on? What must R be?
Greater than or equal to 0, smaller than or equal to total number.
Have I given you a total number? No. So imagine you keep flipping a coin, and I will give you $1 every time it comes up heads. But once you get R failures, the game stops. What's the maximum amount of money you could win? Could you win $1 million? Yes, if you've read Rosencrantz and Guildenstern Are Dead, you can have very long strings of heads, heads, heads. Is it likely? No. So I think Tom Starwood was taking some mathematical liberties with the text when he had over 90 consecutive heads in the tosses of coins. But is it possible? Yes. My exposure is bad. I could easily owe you guys $1 million. Well, not easily. The odds of 1 million consecutive heads is so small, I'm not worried. But we could ask, what's the expected value of this game? If I give you $1 for every success, that's counting the number of successes. How much do you want to pay to play this game? Okay, you want to pay $0 to play the game, sure. I'm not going to play the game for $0. Do you think the amount of money you are willing to pay the game is a function of R? If R is very small, do you want to pay a lot or a little? A little. If R is huge, do you want to pay a lot or a little? Well, I guess you always want to pay a little, but are you willing to pay a lot if R is large? Yes. If you're allowed to get 100 failures, then you can be reasonably confident of getting maybe 100 successes. So you'd easily pay $50 to play. So what are the possible values for R? You might be able to get away with it could be. I don't want to get into the argument of could R be 0. Let's just take R to be a positive integer. And P will be in the interval 0, 1. So you always want to know where do your parameters live, what are your possible values. So let's try to analyze what is the probability that x equals k. So we want to have exactly k successes before we have R failures. Right? As an aside, before we analyze this, in honor of some recent baseball stuff, let's analyze some information about team successes. So imagine I tell you you have won 3 of the last 4 games. And I'll assume that you're playing reasonable teams. This is taken in the middle of the season. What's your winning percentage? 75%. Is that a good winning percentage? Do you think you'll make the playoffs if you win 75% of your games? Yes. Baseball, absolutely. No team, even the great Red Sox this year, are not playing 750 ball. Basketball, you can get a few teams around 750, but 750 should be enough. Hockey should be enough. Football should be enough. Yes?
Can you also say you won 3 of the last 5 games?
So let's look at what's going on. If I tell you that you've won 3 of the last 4 games, so why must you have lost your 5th game?
Otherwise, you would say you won 4 of your last 5.
Otherwise, I'd say you won 4 of your last 5. So who can complete the following phrase? There's lies, there's damned lies,
And then there's statistics.
and then there's statistics. Okay? You need to be careful about how people present information to you. People frequently have agendas. When I was an undergraduate at Yale, there was a grade strike where the TAs absconded with final exams and final papers and refused to grade them or give them back to the professors until their demands were met. Didn't really bother me because I was a science geek at this point. All my classes were essentially science classes, and the science students were not part of the strike. But when I was home, they interviewed 2 graduate students at Yale and asked them, how do you feel about the strike? And it said, Robin Brown, grad student, Yale University, and something similar for the other person. And they talked very intelligently about what the issues were and why the grad students were upset and why they were doing all this. The reporters did not lie, but nowhere did they mention that she was actually the president of the striking organization and the other person was the vice president. Now, it's quite possible during the strike that the president and the vice president will have a lot of things to talk about. And I can easily see the 2 of them walking together on campus. But it was presented in a very misleading manner to make us think that these were 2 generic grad students. It just said grad student. It didn't say president of organization behind the strike. So whenever anybody gives you information, you always want to ask, what's your perspective? Why are you giving me this information? Why are you choosing to give me this information? They must have lost 5 games ago, almost surely, or I would have said they've won 4 to 5. What happened 4 games ago? They won. If they had lost 4 games ago, what would I say? They've won 3 in a row. So now all of a sudden in the last 3 games, they're 2 of 3 for 66%. And in the last 5, they're 3 of 5 for 60%. I am cherry picking exactly where to focus to make things look as good as possible. People do this all the time. I will send you a clip from one of my favorite shows, Yes, Prime Minister. It's a wonderful British comedy where they want people to support a certain position, so one of the people says, I'll just commission a poll. How do you know you're going to get the result you want? Well, you just ask a couple of leading questions, and then you only report the final question. You go, what about the reputable firms? Oh, there's very few of them. And they give an example of 2 different sets of leading questions to get you to say yes or no for the 5th question. You've got to be careful in how information is presented. Okay? So going back to the negative binomial, there's a reason I wanted to give this example. So we want them to have exactly k wins and exactly failures. So I have, here's 1, here's 2, here's k plus r. What must have happened at location k plus r? What must have happened?
Must be a failure.
It must be a failure. Because I'm going until we get exactly r failures, and then I stop. So the last one has to be a failure. So now we know over here, going up to k plus r minus 1, in this range, we have k successes, and we have r minus 1 failures. How many ways can you choose the locations to be the k successes? So it's going to be, what is it? K plus r minus 1, choose k. And then what's the probability of each one of these being a success? P to the k. And then what about my failures? So it's 1 minus p to the r minus 1, but then I have the failure here, which is another 1 minus p. And then in an algebraic burst of insight, we're going to combine the 1 minus p to the r minus 1 and the 1 minus p. And then just say, we know we have r failures in this whole string, so it's just 1 minus p to the r. And so k is in 0, 1, 2. And that's my probability density function. Once you know the probability density function, everything you now want to know is in principle computable. The algebra may be painful. And what makes the algebra look particularly bad here is we have a binomial coefficient with action in both the numerator and the denominator, upstairs and below. Oh well. So we can now try to calculate things like the mean. But before we do that, I always like to take something new and ask, is this related to anything we've seen before? So I'll try to put this back in focus. Can anybody give me a good value of R to study? 1. So if we take R equals 1, then the probability that x equals k is now just k plus 1 minus 1, okay? Let's write it out in its full glory. So that's it in its full glory, right? After we simplify, it just becomes p to the k 1 minus p. What does this look like? Geometric. So this is just geometric with parameter p. So the negative binomial when I equals 1 is just the geometric. Okay? You can then ponder why it's called the negative binomial rather than maybe like a negative geometric. But you do have the binomial coefficients coming in, and you do have that choosing process going here. So that's probably the justification for the binomialness in the name. But again, whenever you have something, try to look at, is there a case I know? When we get a formula now for the negative binomial, we can test and see, hey, does this formula work in the special case when r equals 1? We've already done the geometric distribution. We know what the answer is. We can then check and see if everything is correct. Right. Any questions on up till here? All right, so let's look at the calculation to calculate the mean. So x is negative binomial r comma p. So the expected value of x is going to be the sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, 1 minus p to the r. We could try to do this calculation directly. And we could try to expand out the binomial coefficient, and maybe the k cancels down there, and maybe we play some algebraic games. I think I do this in the book. I have no desire to do this. If you have a desire to do this, we need to talk. Okay? You should not want to do this much algebra. What should we want to use? I'm sorry? You could do this with linearity of expectation. But today, what am I focused on and fixated on today? Today I love differentiating identities. That is my hammer. Whatever problem I am given, I am going to make differentiating identities work. So instead, we need an identity. What's the only identity that you can really think of that must be true for probability distribution?
The infinite sum equals 1.
Yeah, we always have this. The sum, k goes from 0 to infinity, of k plus r minus 1, choose k, p to the k, 1 minus p to the r equals 1. This is a really good choice for your identity in any problem you're looking at. If it doesn't work, utter some curse words and try something else. But this should be your go-to. Now we want to apply p d by dp. And if we do that, we're going to bring down to k, which is great, but crap, we're going to have to use the product rule. How can we avoid the product rule?
Pretend it's Q.
Well, we could try to pretend it's q, but if we pretend it's q, we would then have to have this side here now depends on p and q. So this is in some sense a simplification in the case when p equals q. So you are welcome to do that. That requires intelligence and thought and work. Things I like to avoid if at all possible. I am lazy. I'm not saying you can't do that, but you would then have to go back and you would have to find a formula that works with this replaced with q.
Take out the 1 minus p to the r and put it on the side.
Yes. When you said take out, I thought this was like a hit going on, but yes. Move this over to the other side.
Just get rid of it.
Just get rid of it, you know. Don't ask any questions or you too can vanish. I can drop a house on you. People at least know what that is a reference to. I Can Drop a House on You. The best description of this movie is a young girl travels to a strange psychedelic landscape and kills the first person she meets, and then teams up with 3 complete strangers to kill again. Wizard of Oz. So we just move it over to the other side. Now if we apply P d by dp, we're not going to have to worry about the product rule. We do have to worry about the fact that it's an infinite sum, but what class saves us? What class saves us? When in doubt, real analysis. Yeah. Whenever you need anything to be rigorously justified, real analysis is almost always the answer. And so with real analysis, you can justify this, and now you get the sum, k goes from 0 to infinity, of k plus r minus 1 choose k, p to the k is equal to p. Now when I take the derivative of this, I'm going to get a negative coming down from the negative r, and I'm going to get a negative coming here, so the negatives will cancel. So I get a p r to the 1 minus p to the negative r minus 1. What should I move over to the other side? To what power? To the negative r. Because that's what we need to have our probability density here. So then this becomes the expected value of x is the sum, k goes from 0 to infinity, of k plus r minus 1 choose k, p to the k, 1 minus p to the r, and then this will just equal r times p over 1 minus p. So that will be your expected value. And with a little bit of work, you can calculate the variance as well. If you take the special case when r equals 1, this does reduce to our geometric formula. So when r equals 1, it's consistent. This does not mean we haven't made a mistake. Yes?
This isn't a mistake.
Okay, good. I was about to say, I thought this was consistent.
This might, like, that kind of suggests that maybe, like, this is the same as a sum of, like, r geometric.
Right. So there is an interpretation going on here. What you can do is you can let y1, y2, yr be geometric random variables with one failure. And you keep going until you get your first failure. And so what this is saying is that if x is the negative binomial, x is really the same as y1 plus y2 plus yr. And if you notice this, this is actually going to really help you on, I believe, one of your homework problems coming up. That I can view this more complicated process as a bunch of simple ones, and then I can use the linearity of expectation. And in fact, if you look at this, it's r times that, so that should suggest maybe you have some process going on. But it makes sense. If you're waiting for r failures, to get to r failures, you first have to get to 1 failure, and then to 2 failures, and then to 3 failures. So you could just keep going until you get a failure, and then that ends the first process. And then you go again until you get another failure, and that ends the second process. And so now, this is a little bit more advanced. What do you think happens as r goes to infinity? What do you think the distribution of x goes to? So as I take more and more of these, as r gets larger and larger and larger, what do you think this sum will converge to? Can't be many possible answers if I'm asking. Yes? It should be a normal distribution. I'm having a sum of independent, identically distributed random variables. It should converge to normal. So now we have this beautiful theorem that as r goes to infinity, somehow these coefficients must be such that most of the mass is concentrated near the mean. And the mean is going to be, k is about r times p over 1 minus p. So in the special case, when p equals a half, this tells you the mean number of successes is r. Well, that makes sense. I should have about as many successes as failures if p is a half. So this is a really nice random variable, you can often look at this as maybe how long will you last until system failure. Maybe you have lightning strikes, or maybe you have mechanical problems, and you can survive a certain number of them until your system is just compromised. How long do you expect things to last? Well, the higher probability you have of success, the longer you'll be able to last. Because then 1 minus p is going to get really small in the denominator, and that will bump you up. And the more failures you can survive, the longer you will last. So this is something that's used to model a lot of things in the real world. Okay. Any questions on the negative binomial? Okay. So now it is time to turn to the standard normal, or more generally to any normal random variable. This is the most important distribution, I think, in the class. And we've talked numerous times about how sums of independent identically distributed random variables converge to being normally distributed. We will prove that later. But this is telling you why this is so important. One of the things I want to emphasize in the course is why this is true. So if there's time, that handwriting should be sloppy enough that nobody should be able to read that. So if there's time, I will get to that later. So we will say x is normal with mean mu and variance sigma squared if the density function is equal to 1 over square root of 2 pi sigma squared, all under the square root, e to the negative x minus mu squared divided by 2 sigma squared. Now, notation gets reserved. When you see the letter mu, what should you be thinking? Mean. And when you see sigma squared, what should you be thinking? Variance. I should not be allowed to do this unless mu is the mean and sigma squared is the variance. So, one of the first things we prove is, yes, mu is the mean, sigma squared is the variance. This is clearly non-negative. We have to prove it integrates to 1. I'll prove it integrates to 1 only in the special case when mu equals 0 and sigma equals 1. You can do change of variables from calculus and do the general case. All right. So the idea is the polar trick. I will review a little bit of two-dimensional change of variable formulas. So let's let I be the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 dx. And the claim is I is 1. We want to prove that. So rather than proving I is 1, I'm going to prove I squared is 1. So I squared is equal to minus infinity to infinity, 1 over the square root of 2 pi e to the negative x squared over 2 dx. And then I'm going to use a different variable. I'll use 1 over the square root of 2 pi e to the negative y squared over 2 dy. Okay? More scribbles for myself. This is the same as the double integral, minus infinity to infinity, minus infinity to infinity, 1 over 2 pi e to the negative x squared plus y squared divided by 2 dx dy. When you see this, if you have taken a good Calc 3 class, it should be screaming a change of variable formula to you. The integrand only depends on x squared plus y squared. This is one of the greatest examples of sometimes you take one step backwards to take 2 steps forward. I want to solve a one-dimensional integral. I'm going to convert it to a two-dimensional integral. This at first seems foolish. The reason this is not foolish is we actually have some techniques we can use for multivariable integration. And because this only depends on x squared plus y squared, so we let x be cosine theta, we let y be sine theta, and then dx dy transforms to r dr d theta. How many people do not remember the r dr d theta? Okay. Have you seen this in multivariable? Okay, so you should not actually write it as r dr d theta. The way this should be written is it should be written as dr times r d theta. Because this, if you think of x and y as being in meters, this is meters squared. This is the unit of area. Theta is in radians. Theta is unitless. So if I look at dr, that's in meters, and then r d theta, that's an arc length. So let me draw a circle. Let me draw an egg that is supposed to represent a circle. All right, so here's a circle. Here is a slightly larger circle. Here's my radius r. Here's r plus delta r. Now, here's my angle theta. Here is an extra angle of delta theta. So what I'm doing is, rather than using rectangles dx dy, I'm breaking things up into sectors. What is going to be the area of this sector? Well, the whole circle, it's pi times the radius squared. So if I take the big circle, the radius of the big circle is r plus delta r. The radius of the smaller circle is r. So the big circle is pi r plus delta r squared. I subtract off the smaller circle. And that will give me the entire ring. How much of the ring do I get? I get delta theta over 2 pi. If delta theta was amazingly pi over 2, I'd get a quarter of the circle. If delta theta was pi, I would get half the circle. So the fraction that I get is delta theta over 2 pi. This is a really quick return to Calc 3. Well, now if I multiply things out, I get pi r squared cancels the pi r squared. So I'll get 2 pi r delta r plus pi delta r squared divided by 2 pi times delta theta. So the first piece becomes r delta theta, and the next piece becomes 1/2 delta r squared delta theta. As we take the limit as delta theta and delta r go to 0, the first piece becomes a r dr d theta. And the second piece has an extra delta r. And so this piece, no contribution in the limit, because it's got 3 pieces, not 2 pieces. Okay, so in the limit, those lower order pieces don't matter. And this is a sketch of why, for polar coordinates, the conversion factors dx dy goes to r dr d theta. Okay, so knowing that, we can now go back to our integral I squared. And so now we get I squared is the integral of 1 over 2 pi e to the negative r squared divided by 2 r dr d theta. So theta goes from 0 to pi, r goes from 0 to infinity. Because x and y went over from minus infinity to infinity, so that was the entire plane. So we get the entire plane. R goes from 0 to infinity, theta goes from 0 to 2 pi. Well, you basically can't live better than we live here. There's no r and theta mix up together, right? They're separate. So I can write this as I get my theta integral. Theta goes from 0 to 2 pi. I can even pull out the 1 over 2 pi outside the integration, d theta. And then r goes from 0 to infinity of e to the minus r squared over 2 r dr. All right? So I integrate d theta from 0 to 2 pi. What do I get? I'll just get 2 pi. And now talk about living life well. You should be worried about an e to the minus r squared. That's tough to integrate. The only way you can integrate an e to the minus r squared is if you happen to have an r dr. And we get that precisely without change of variables. Not only that, but we don't even have to worry about the 2 that comes down because it cancels with the 2 there. We do have to worry about the minus sign. So we get e to the minus r squared over 2, and the minus sign flips the order of evaluation. All right, well, e to the negative infinity, not worried about that. It's going to just be 0. That's going to be 1. So when the dust settles, you get 1. And it is a probability distribution. Okay? Absolutely spectacular result. If you want, you could do some analysis earlier to prove that this integration is actually possible, that the function decays sufficiently rapidly. If you've never seen e to the negative x squared before, well, once x is at least 1, you can bound it by e to the negative x. And we know the exponential function decays fast enough to integrate, so the e to the negative x squared, which is decaying even faster, will also be fine. So how many of you had never seen a proof of the normalization constant for the Gaussian? Okay. So you've at least now seen that this is actually the correct normalization. Now we want to do the next step, and we want to show that it really does have mean mu and variance sigma squared. Okay. Oh, technically we just showed I squared equals 1. We didn't show I equals 1. We have to take a square root. We know this is non-negative, so it's not going to be the negative 1. All right. So the next question is, how do you calculate the mean? Well, I claim that if you can do some change of variables, it's again enough to just do the case mu equals 0, sigma equals 1. So I'm going to just do those as much as possible and leave the rest for you as an exercise. So if I want to calculate the mean is actually not so bad. Minus infinity to infinity of x, 1 over square root of 2 pi, e to the negative x squared over 2 dx. What does this equal? 0. And unlike the Cauchy distribution, the decay is so rapid, it doesn't matter how I go to infinity, we're going to just get 0. This is an odd function, and it's integrated over a symmetric region about 0. All right, if I want to calculate now the expected value of x squared, that's going to be harder. So now I have x squared, 1 over square root of 2 pi, e to the negative x squared over 2 dx. One way to do this is to integrate by parts. So when you integrate by parts, you have to choose what is u and what is dv. And you've got essentially an x squared to play with and an e to the negative x squared. Do I want this to be my u or my dv? Do I want this to be my u or my dv? So if I differentiate this, I can do that, but that's going to bring down a power of x. And if I integrate this, that's going to increase the power of x.
If you make ux and then dv.
Yeah, so what we want to do is we want to make ux and dv 1 over square root of 2 pi e to the negative x squared over 2 times x dx. Because if we put the x here, we can now integrate this, and now we're not going to have the power of x increase. So if we do that, we will be fine. I will leave the rest of the calculation to you to do, and then you will get that this just is equal to uv at negative infinity, infinity, minus the integral from minus infinity to infinity of v du. So the details are in the book. I will leave the rest of that calculation to you to do. Well, how else do you think we could solve this and calculate the variance or calculate the second moment? Yes? Differentiating identities, right? Yeah, this is what I'm fixed on today. There's got to be a way to do this. And so sometimes, if you want to solve one problem, it's actually easier to solve infinitely many problems and embed it in a class. Rather than trying to find the variance of the standard normal, let's find all of them. The mean is no problem. It's just translating everything as a change of variables. So let's consider the integral from minus infinity to infinity of x squared 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. So we always have to start with an identity. Our identity is going to be the integral from minus infinity to infinity. Oh, sorry, I need a sigma squared here now. Of 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx equals 1. So that's the identity. It's a probability distribution. It integrates to 1. What operator do I want to apply? The derivative with respect to what? So what do I want to take the derivative with respect to? Yeah, Sigma is the only thing that's floating around here. X is a variable of integration. And if I take the derivative with respect to sigma, when I take the derivative of this exponent, an x squared is going to pop down, which is exactly what we want. But we're going to have a product rule because we have a sigma here and a sigma there. So let's move this over to the other side. So you get the integral from minus infinity to infinity of e to the negative x squared over 2 sigma squared dx equals the square root of 2 pi. I'll just have the sigma outside like that. Now, let's apply sigma d by d sigma. And I get minus infinity to infinity. When I take the derivative, I'm going to have a negative x squared over 2. Then I've got to take the derivative of sigma to the negative 2. There'll be negative 2 sigma to the negative 3. E to the negative x squared over 2 sigma squared. And I'm multiplying by a sigma. And then on this side, I take the derivative. It goes away. I multiply by sigma. It comes right back. So actually, when you leave it inside the square root, it will be a 2 pi sigma squared. All right, sigma cubed. That becomes a 1 over sigma squared. I'm going to move that to this side, and I'll move the 2 pi sigma squared over to this side, and I will get the integral from minus infinity to infinity. The negatives cancel, the 2's cancel like this good. X squared, 1 over square root of 2 pi sigma squared. E to the negative x squared over 2 sigma squared is equal to sigma squared. And since the mean is 0 in this case, we get the variance is just the second moment is sigma squared. Everything is consistent. As an exercise, you can then keep taking higher and higher moments. And it's a really nice exercise to show that the expected value of x to the 2m plus 1, an odd number for the standard normal. Oh, somebody's phone went off? Somebody will be providing munchkins on Monday. All right. What do you think all the odd moments will be? 0. And that you just get by symmetry. The even moments is just 2m minus 1 double factorial. Where 6 double factorial is 6 times 4 times 2. 7 double factorial is 7 times 5 times 3 times 1. You just multiply every other as you march down. So it's a nice exercise to prove this. You can do this with integration by parts. You can do it with integrating with differentiating identities. There's lots of different ways of doing this. All right, I think we've got about 1 or 2 minutes left. Okay. So I wanted to just go over one quick scribble. And so one of the things you've got to be very careful about is, did we talk about how you can combine exponents? E to the x, e to the y is e to the x plus y. Did we mention that in this class? Right. Just as a warning, e to the x times e to the y is e to the x plus y. But what the left-hand side means is the sum, m goes from 0 to infinity, of x to the m over m factorial times the sum, n goes from 0 to infinity, of y to the n over n factorial. And this is the sum, k goes from 0 to infinity, of x plus y to the k over k factorial. It is not immediately clear that this is true. This is our definition of e to the x. E to the x is this infinite sum. So if I have e to the x times e to the y, I do not initially know that it is e to the x plus y. That is only the result of much work. So with some algebra, you can show, well, let's just group all the x's and y's. I'm going to do this really fast, such that m plus n equals L. So I'll sum L goes from 0 to infinity, and then I'll have x to the j, y to the L minus j, divided by j factorial, L minus j factorial. J goes from 0 to L. And if you look at this, this is looking a lot like a binomial coefficient. So I multiply by an L factorial here. I divide by an L factorial here. If I then look at this here, this is then going to just become x plus y to the L. And so you'll get, I should use the letter K. Oh, well. We get the sum, L goes from 0 to infinity of x plus y to the L over L factor. It has to be proved, but it can be proved and it justifies the notation. All right, this is a good place to stop.